everyone. So the last video lecture, we talked about the Cauchy-Riemann equations, which basically related the complex derivative of a function to the partial derivatives of its real and imaginary components. And today we're going to talk about some applications, sort of the first kind of easy application of these equations. So let me remind you the setup. We've got some complex function from the complex numbers to the complex numbers, or maybe a little more generally, if f is not defined everywhere, it's defined at least on some region G. And just to remind you, a region means an open, connected subset of C. And so what you should think of is like an open disk. Usually that works. So if we have a complex function, let's assume that f is holomorphic on its domain, so on all of G. And remember, this just means that the derivative f prime of z is defined everywhere. So for all points in the domain, for all z inside of G. Okay. So the derivative is defined as a limit, and we're assuming that that limit exists, and so this derivative is well defined for all points in the domain of the function. Remember, we can think of this limit as, sorry, what am I trying to say? So it's defined as some limit as h goes to 0, and you can approach 0 along lots of different paths. And the Cauchy-Riemann equations came from just looking at the horizontal and vertical paths, right? And if you choose those particular paths, you get a particular expression for the derivative in terms of partial derivatives with respect to x if you're going along the x path, or with respect to y if you're going along the y path. So let me just remind you what the Cauchy-Riemann equations say. So we can write f of z in terms of real and imaginary parts. So z is equal to the sum of its real and imaginary parts. Let's write that x plus iy. And then the output of f also has real and imaginary parts, so I'll call those u and v. And so if we write f this way, then u and v are two functions which go from the plane to r. And the Cauchy-Riemann equations say that if f prime of z exists, then it equals, if I choose a path, a horizontal path, then it's equal to just taking the partial with respect to x, which we calculated was the same as the partial of u with respect to x plus I times the partial of v with respect to x. On the other hand, if we calculated the limit by taking a vertical path where we are going along the imaginary axis, then it also equals, it also equals the partial of f with respect to y, because we're only varying the y part. And we calculated this to be, the partial with respect to y divided by I, because we're dividing by h, and h is imaginary, and this is what came out. And so if we do this way of computing the derivative, it's equal to the partial of v with respect to y plus I times the negative of the partial of u with respect to y. And so what the Cauchy-Riemann equations say is that if the derivative exists, then both these expressions have to be the same expression. In particular, these two things are equal, and these two things are equal. And so we get some relation between the partial derivatives of u and v. Okay. So one sort of obvious implication of this is the following. If the derivative of f, the complex derivative of f, is 0, in some region of the domain, then that just means all the partials, then like this has to be 0, this has to be 0, this has to be 0, this has to be 0. So all the partials of u and v must be 0. Okay, and what we want to say next is something that is pretty intuitive. In that case, the function f must have been a constant function. And the way we're going to conclude that is by showing that both u and v have to be constant functions. So let's consider u first. So u is a function of x and y, which I'm thinking of as real coordinates, and its output is a real number. So it's a function from R2 to R. And I claim that the partials ux and uy are 0 on the domain. So, maybe the domain's not all of R2. Maybe it's some region G, which when I say region, I mean it's connected, which is actually pretty important. So here's G. This is going to be the domain of my function u. Now, let's think about what it means for the partials to be 0. So the partial of x being 0 means that if I fix some y naught, I keep the y value constant, and vary x, then if I'm keeping y constant, then u is just a function of a single variable x. And what that corresponds to is choosing some y naught and looking at the function u, but just restricted to a horizontal line with a fixed y naught value. So we can look at different fixed values of y naught, which just means we're looking at horizontal lines in the domain. And let me write what I was saying. So if I fix y, then u of xy naught is a function of one variable, namely x. And then from regular single variable calculus, we know that if the derivative of this single variable function, which in this case is equal to the partial with respect to x, is equal to 0, that implies that u is constant. And in this case, we fixed the y naught value, so this is saying that this function is constant as I vary x. It's constant in x. Right? And what this means is u is constant along these horizontal paths. But similarly, I could fix x to be some value x naught, vary y, then if the partial with respect to y is 0, this implies that u is constant in y, which means it's constant along vertical paths. vertical paths in the domain. So if both the partials are 0, then it's constant. The output of the function is constant as I move in horizontal paths. It's also constant as I move in vertical paths. And you can see that this means that it must be constant on all of the domain, because if I choose some point x0, y0 here, maybe some other point x1, y1, I can travel from x0, y0 to x1, y1 along a sequence of horizontal and vertical paths, and u had to be constant along this vertical path because its partial with respect to y was 0, but then it's constant along this horizontal path, then constant along this vertical path, etc., etc. So the value of u is not changing as I move on this purple path, which means its value has to be the same at both of these 2 points. That's true for any 2 points. And so finally, this implies that u is a constant function. So the proposition, so the same thing is true for v, right? There's nothing special about u. If we look at the imaginary part v, then if its partials are both 0, then it has to be a constant function as well. And so the proposition that we come up with is that if f is holomorphic, which just means its derivatives exist everywhere on a region G, then if the complex derivative is always equal to 0, for all z inside the domain G, then f is a constant function. And the way we proved that is we showed that if f prime is 0, then that means its partials, the partials of u and v with respect to both x and y must be 0, which implies that both u and v have to be constant. But f is just a sum of u plus iv, so if u and v are constant, f is constant. So that's the proof. So that's not so interesting, I guess, because it's probably exactly what you would expect if you have experience with calculus of real numbers. But it actually has some really interesting consequences in the land of complex numbers. So corollary to this proposition is something that is a little more surprising. And this is exercise 2.20 of the textbook, which I'll just prove now. So the corollary is the following. So the setup's the same. This is a holomorphic function. So its derivatives exist on everywhere in the domain, and G is a region, which again just means it's connected and it's open. Then I claim that if f of z is always real, so if the output of this function is always a real number rather than a complex number, so the imaginary part is 0, then it turns out that f has to be a constant function. And this is telling you that being differentiable is a really strong condition, because it's saying that if you're differentiable and your outputs are always real, then actually you were just a constant function to begin with. And the proof here, again, uses the Cauchy-Riemann equations. So if f of z is real, well then its imaginary part is 0, right? And again, we're going to write f in terms of its real and imaginary parts, so I'll write this as u plus iv. But if f of z is real, then that's saying that the imaginary part is 0, and the imaginary part is v, right? So the output v of xy equals 0 for all points of the domain. So for all z equals x plus iy in the domain G. So v is 0, right? But by the Cauchy-Riemann equations, since f was differentiable on the whole domain, it has to satisfy these Cauchy-Riemann equations. The Cauchy-Riemann equations say the partial of u with respect to x is equal to the partial of v with respect to y, and the partial of u with respect to y is equal to the partial of v with respect to x with a minus sign. Okay. But if v of xy equals 0, then of course its partials are also 0. So this is 0, and this is 0. And this implies that ux and uy are 0, which, as we just saw, implies that u is a constant function. So u of xy equals some constant c. But then that tells us, look, v is 0 and u is constant. That means f was just a constant function to begin with. And that's the proof. And so already this shows you that a lot of functions can't be differentiable in the complex sense. So for example, we looked at that function previously defined by, so maybe I'll write, consider the function f of z is equal to the real part of z. In other words, f of x plus iy is equal to just the real part, which is x. So this is a real valued function. The outputs are always just real numbers. So this function is defined everywhere on all of C. And this is saying that it cannot be holomorphic. In other words, its derivative, complex derivative, can't be well defined everywhere because it's a real valued function, but it's not a constant function. And what we just proved is that if a function is differentiable and it's real, then it has to be constant. Here we have a real function that's constant, but it's not, sorry, we have a real function that's not constant, which means it's not differentiable everywhere. So this is already a pretty surprising and useful application of the Cauchy-Riemann equations, and we're going to see a lot more later. By the way, this same argument also, you can do a really similar proof to show that if you have a function that's purely imaginary in its outputs, then it also has to be a constant function. I think I'll end there.